not supposed to be able to change it. And there might be some rare exceptions out there, but this stays like a general rule of thumb. You're not supposed to be able to change anything. And ledger is really just super fancy for list. It's like it's like Old English for list at this point. So that's what a blockchain is. Now, if you follow the news, you'll hear a lot of companies and organizations, they really want to use blockchain, and it's great for media hype. You know, everyone jumps on it, like, oh, you hear JP Morgan launches their own blockchain. We're gonna, you know, everyone's like, whoa, you know, the company's really getting with the times. Nah, that's garbage, man, I'm telling you right now. But anyway, I digress. So there are some applications that blockchain is super good for. Like, I highly recommend it. Transparency. I know there are some products out there that promise using blockchain. IBM was using it to monitor a batch of coffee beans, I think, from Colombia, and it was a pretty huge success. Institutional spending, there's this idea of decentralized organizations that don't require a single server or entity to control them. That's a super good application of blockchain. Once again, the decentralization comes up all the time. Voting, public opinion. There's a token you can check out called Augur, A-U-G-U-R, and it's used to sort of get an idea of public opinion. You can put a poll out there and get some pretty interesting results. And asset management, this idea of tokenization. I know there are some retailers that are looking at it. It's where you can take some kind of object and you can represent it with a digital asset, which makes for a really neat little ecosystem. What I would really caution against using blockchain tech for is data storage. Despite the transparency, it is incredibly costly to store anything on a blockchain, and it's very slow. You're going to end up shooting yourself in the foot more often than you're going to end up doing something useful for yourself. So, word of caution. Anything fast. So if you want like a game that, I don't know, uses blockchain, don't rely on it too much for like super fast chat or applications or anything. Blockchains are by nature not meant to be the most fast things on the planet. They're meant to be secure and transparent. That's the first thing they focus on. So if you want to do high frequency trading with blockchain or some FPS games that use blockchain as their backend, I gotta caution you against that. That's just my 2 cents. All right, so what the heck is this? What the heck is this Ethereum thing I keep mentioning? So Ethereum is, some people call it blockchain 3.0. It's meant as a successor to Bitcoin, which we see as like the foundational framework for, I don't know about you, but you can get a lot more cooler stuff done with this than free shirts. My personal opinion. I digress. So we had blockchain 1.0. Which gave the idea of blockchain, like, okay, you can have all this data and you can have it in a decentralized manner. We got the fundamentals down. But people realized pretty soon, like, oh, wait a minute, 1.0's got some problems here and there. You got the 51% attack, you have hardware that's getting centralized, and we don't want that. So then you had 2.0, some people were busy mixing hash functions and they were like forking Bitcoin all the time, and you heard of these garbage scam coins. And then we have 3.0, so that's where Ethereum is. And we look at things called smart contracts. So the smart contracts relate very closely to the idea of what I call a state machine. So the people behind Ethereum realized, oh, if Bitcoin's this huge decentralized entity, then you can theoretically treat that entity as a kind of like state, like it's a 1 or a 0, where there's a certain set of instructions, and you can map that out throughout your contracts. So what happens is you can write these applications that run on all kinds of machines. It's like an abstraction layer. Super high degree of concurrency, meaning that if one thing goes down, everything else still works. It's a really nice feature. I mentioned tokenization earlier, so I won't spend too much time on it. It's not the focus of our workshop, but it's definitely something to check out, especially for any hackathon-related projects. It makes for a really neat little tool. The IPFS, I mentioned at the very beginning, is the Interplanetary File System. So it's like blockchain, but for the internet. And it tries to address some of the main problems we see in the internet today. I mean, sure, the internet's fast. You can watch videos of cute kittens and puppies. I'm partial to that myself. But at the same time, there's a growing concern over this centralization. I give an example. In 2012, Turkey opted to try and shut down Wikipedia in its entirety. So IPFS comes out as this idea that you don't have to have a single entity to store data. And I mentioned earlier, like, it's very prohibitive to store data on a blockchain. Well, IPFS is your sort of, it's like a backdoor. It's a bit of sleight of hand, like a magic trick. You can sort of funnel your data through IPFS, but you keep the key to the data on your blockchain. And you'll see how that works. I'll get to it real soon. In terms of features, I mentioned decentralization, deduplication. So what that means is, let's say like I got a file somewhere, like maybe a picture of me, and then you upload a picture of me. Well, that's a bit of a waste of space, isn't it? So IPFS is smart enough to notice that there are two identical files, and it'll automatically remove the deduplication. Saves a lot of space, saves a lot of resources. It's very secure, so a lot of blockchains work on this idea of a hash function. IPFS also uses this hash function as well, but it serves a dual purpose. It lets you identify or locate where stuff is, and it also lets you ensure file integrity, meaning that if I were to, I don't know, change my file and insert a virus or something, you wouldn't get the file because the hash is permanently changed. It's a very neat little dichotomous sort of protection mechanism. And then we have SALT, or sodium chloride, for your chemistry majors. SALT is not supposed to be a focus of this workshop, but it is something I want you guys to have in the back of your mind. A lot of people think, oh, blockchain has this transparency. But at the same time, you hear blockchain being used for medical records, for, I don't know, driver's insurance or your ID, and then you get this sort of conflicting image in your mind. Like, wait a minute, if this is supposed to be the most open thing in the world, how do you hide data on it? Well, that's where SALT lets you use this public key cryptography system. And I think it's easier if I actually show you the code later to understand how that really works. It's not a complicated concept, but it's definitely very useful if you have some sensitive data that you'd like to transmit or store on the blockchain. So we do have some tools. You'll find these especially relevant for Ethereum development. There are some other decentralized platforms like EOS or Tron. They have their own set of tools. So there's Truffle, Ganache, MetaFox, and for those of you who are like huge Node.js or JavaScript junkies, we have plenty of that stuff too. So I'll go ahead and explain it. Now, I mentioned all those pitfalls for Bitcoin and blockchain tech. Like, well, if there are all these pitfalls, what do we even use it for? And I've built this demo application to try and show you guys what one potential use of it might be for. And I call it Sifter, or the Secure File Transfer. It's built using all the tools that I showed in the previous slide. And it basically just lets you upload and send a file intended for a single recipient in a very secure fashion. It's very cheap too, I would argue, because one of the huge problems with data storage and sending large files is the fact that you incur a huge cost for hosting and for centralization and all that stuff. So we'll see how we can do that. So we have our main tools: Truffle, Ganache, and MetaFox. Truffle is available through NPM. I mentioned the smart contracts earlier. That's like how you write an application for Ethereum, pardon me. And it lets you create this really comfortable environment for developing Ethereum code. And it lets you debug and test it before you launch it. There have been some very famous incidents where people have not tested the code properly, or they didn't. Right, it looks like we had 2 people leave for ice cream, and it hurts here, but it's okay. You roll with the punches. That's a common theme in DApp development, I might add. So Ganache is your way of simulating the blockchain. So if you the smart contract. I'm terribly sorry if my explanation for that was a little shoddy. So your smart contract is like the smallest executable unit for these decentralized applications. Like you write a smart contract or you write multiple contracts, and you can link them together. And when you have your decentralized application, you link your user interface to those contracts. The contracts live on the Ethereum blockchain, so there's no central server. You don't have to worry about some server crashing and like, uh-oh, now your 30,000 users are offline. You don't have to worry about that. That's like the huge selling point for Ethereum. So that's what a smart contract is. You'll see an example very soon. right? So we've got a question here. A smart contract is analogous to a transaction. They are closely related. Like when you deploy a smart contract, it's considered a transaction. Like the act of sending or moving anything on the blockchain is a transaction. But the actual thing being transacted, we would call that the smart contract. And the smart contract almost acts like a dummy, like a virtual dummy person that lives on the blockchain. Like you send it data and you ask for data, and it'll just do its orders blindly. But it does it very well, and it does it very securely. So that's the huge selling point. MetaFox is your Chrome plugin. You can use it with Firefox and I think Safari as well. It links or lets you link your Ethereum wallet to your browser. That's how you interact with these decentralized applications. You need to be able to talk or get the bridge between your UI to the smart contract. So MetaFox injects, it quite literally will inject the JavaScript you need to do that stuff. Really neat plugin, makes your life a whole lot easier. There was a time before MetaFox existed. If MetaFox didn't exist, I probably wouldn't be standing here right now giving this workshop. This would be like a whole college course by itself. But I digress. So without further ado, I think I'll just give you a spin of what's going to be built. So here's the GitHub repo. It's just John, my name, ZL-777s. If you get that reference, you're a Linux god. And SFTR, so Sifter, so the secure file transfer. So I'm going to try and show you guys I'm going to flesh it out from the top down. So I'm going to show you what the front end looks like first, and then you're going to see, we're going to go from the front end all the way down to the bare metal. Or as I put it, like, you see what you see what makes the thing you see what's like feels the thing that you see, and then you finally get down to what really drives everything. So let's go ahead and get this, let's get this show on the road. Go ahead and fire up Chrome. I'm going to exit out of this PowerPoint. All right, so this is the terrible user interface that we have for our application. Now, why does it look like, it's made in 1995? I give you a very good reason. The focus of this workshop is decentralized application development. I'm not looking for React. I'm not looking for Angular. Don't get me wrong. I'm a huge sucker for very sexy user interfaces, but that is not what I'm trying to focus on. So what Sifter does is it uses what I mentioned earlier, that public key cryptography system. And you generate, a public and private key for yourself, or every user has their own public-private key pair. And then what you do once you've generated those keys is you can go ahead and transmit your key to the Ethereum network. It's like your email address, it's publicly available. And you're going to need other people to see that key, so that way you can encrypt your files and send them securely. So we have this send file feature. So we say like, hey, send a file to someone. And you just have to take their own address, their Ethereum address, and this private key is your private key. And you're going to use that private key as part of the encryption process. And then there's also like a receive file option here where you put the key in again, and you hit download, and it'll grab the file for you. And what I mean by like the whole public-private key system is, like let's say person A, like I have a public-private key pair, and you might have a public-private key pair. And oh, we got a question, yes? That is true, but then again, I told you this UI, that's not my focus. I'm trying to show you guys what goes on under the hood. The private keys, there's a concern that if you have to use your private key in the encryption process, that you might, it might end up compromising your security. Well, the way SALT works is it's the public-private key or public cryptography encryption system. That's what I was trying to get to the explanation for. So your private key acts as like another signature to prove that it's you. Usually a good app, you won't even see this key stuff going on. Like the best decentralized applications out there, you have no idea what's going on under the hood. Like it doesn't say like, oh, it's a blockchain app, or you want to hide those details from the user because it's something it just makes their head hurt. Yeah, that's the most basic system you're thinking of. So he mentioned like just use their public key and encrypt it. That's like the fundamental system. But the way SALT works, and mind you, the reason I keep bringing up SALT is it's 3,000-bit secure RSA. Like that's it's very fast, and it's pretty damn secure. And I bring up the speed part because a lot of traditional encryption systems you see for browsers, they're going to make your browser hang. Like I could have a text file that's like, I don't know, 10 megs or something. Your browser's gonna sit around for 2 minutes. I don't know about you, but I don't want my user to, you know, sit there for 2 minutes and then. But the private key is not going to actually get transmitted anywhere. We use the math on the private key to get another key, the public key. And Salt just sort of it extends that crypto system. You'll see. I'll give you an example very soon. So if you don't get it now, it's all cool. It's all cool. Yeah. So you go ahead and send your file, and you can receive a file like so. So I'm going to start with our UI. To those of you who have never used an HTML preprocessor, this might look a little weird, but you'll still see all your familiar tags and your fields and whatnot. So I have your headers. I have IDs for all your stuff. You can actually see the HTML. The HTML looks like this. So it's in the GitHub repo I mentioned earlier. You could clone it and you can play around with it. And it's very simple. I've made it as simple as possible because I want to show you guys what's under the hood. I mean, you mentioned earlier you were concerned with the private key. Why the heck is that private key even getting into the system? You'll see it pretty soon. I'm sorry, I can't hear you too well. Can you speak up? I can't hear you too well, but I think you're talking about like a man-in-the-middle attack, or if someone like gets the key, like while it's. Oh, the public key. You don't have to worry about your public key getting caught. It's the private key that you have to worry about. The public key is mathematically derived from the private key. They're not two random keys. They're both very closely related, but they're only related one way. It's like a. Yes, I'm not going to explain the RSA system. The only reason I brought it up is people like to use the number of bits in RSA as like a flex. Like, oh, our crypto system, 3,000 bits of RSA, that's pretty damn good. And I'm like, okay, man, I mean, sure. But then again, RSA is it's one of the first, and it's probably one of the more antiquated crypto systems out there. But I digress. So from our UI, it just makes all the fields you saw earlier, these disgusting, unaligned, Times New Roman, HTML5. There's no CSS here, no React.js. In fact, I go on an aside here. That's the reason I wanted to build it this way. I mean, if you go online right now, the number of tutorials that abuse React is astounding. It is unimaginable. Like, I'm trying to understand what the underlying framework is. And here you are, sprinkling all these cute little buttons here. And I don't need that. I don't want that. I just want to see what goes on under the hood. That's the goal of this workshop. All right, so going from there, there's the JS. Now the JS is actually the really interesting part of this project. That's the bridge you're going to see between your smart contract and the actual front-end UI. So I did mention there were a number of NPM installable tools. First of them is jQuery. I think some of the more experienced JS people will groan at that, but I found it pretty useful. I'm not a JS dev, by the way. That's not my focus. My actual background is C and C++, but I still put up with modern web development nonetheless. We have the two TweetSalt and then TweetSalt util libraries. They're called Tweet because the code itself is only 1,000 or it's 100 lines. It's only 100 lines. It's very small, which is one of the reasons I wanted to use it for this project. And then for the interplanetary file system, you have your HTTP client here. And what happens in we make an IPFS object, and we're going to use what's called the Infura network. And Infura, IPS, if we just go to Infura, there we go. Usually for IPFS, if you want to participate or grab files from it, you have to launch your own node, which means that your user end was going to have to deal with running their own node and hosting some files. That's pretty much the deal. Like you upload something, well, you got to host it, or someone else has to host it. So Infura is very kind enough in that they provide this service for free. and you can just go ahead and grab the this URL and this port number, and just make sure you're using HTTPS, and you don't have to spawn a node. So it's very resource light, and that's going to be our doorway to uploading all our files. Now you see like these 3 chunks here, that's all you need. That's literally all you need to get your decentralized application running with your backend. So you have what's called an ABI, that's called their application binary interface, and that's how you're going to talk from your front end to your back end, to the contract. And then you have your contract address. So you mentioned earlier the difference between a transaction and, say, a contract. Well, in that transaction, when you launch your contract, it's going to give this this address here, and you're going to have to put the address in as part of the app itself. So that way, it'll know how to access it. And all these variables like the ABI and address, those 2 crucial pieces of data, they all go into your contract instance, and that's where Web3 comes in. And Web3 is just, you see this little guy in the corner here? This is MetaFox, and it's my wallet. No, as much as I'd love to, I do not actually have $1,000 and something $100 of Ethereum. I don't, but I'll show you how to make some for testing purposes only. So you have your instance here, and everything else is pretty much related to the UI. I have to mention, I am still a JS newbie, so I know some of you will probably cringe, and you're going to see a lot of unnecessary callbacks and async calls, and I get that. But once again, I'm from a C and C++ background. I like it when my programs run from the top to the bottom, not when they jump from the middle of the file to the top and then back again. That drives me nuts. But I digress. So we have the generate keys function. So in the web page, you saw this earlier. If I go ahead and hit generate keys, it's going to go ahead and give me these 2 32-byte arrays of numbers. And these are generated by Salt itself. There's random number generation going on. It'll deal with all the stuff. And I know I'm going to get harped on because this is a super insecure application. I understand that. But I have to peel away some of that so you guys can see what's going on underneath. You got to have a couple console log statements before you can get anywhere. So there's just it's really this singular call right here: key data, Salt, and then Salt. It's called a box when it encrypts data. So when it provides a public and private key, we call that our key pair. Now here's the interesting part. There is a button here that says, oh, wait a minute, publish your key so other people can use SFTR. So linked to your Ethereum address, which everyone else can see, you're going to have your public key linked to that address. But the reason I hide it is because you don't want your user to have to remember 2 different things just to send something to you. It's like, if you gave me an email and then you had to give me like another number to email you something, I don't know about you, but like as a recruiter, I'd be very offset by that. I wouldn't even bother trying to send an email to you. So that's why you can publish this public key with your address, with your Ethereum address right here, and other people can see it. Other people who call the contract, they can see that information. So if I wanted to send something to you, I can look up your Ethereum address, and I'll be like, oh hey, there's the public key. No worries. I just need to remember one thing.
Does that mean that you can only share 1 file at a time?
Okay, we've got a good question. Does it mean you can only share 1 file at a time? The way I have this preliminary design set up is, yeah, you can only send 1 file at a time, and you can overwrite the previously set file if you wanted to. But it's very easy to modify the internal contract structure so you can have more than 1 file. And it's very cost effective too. Like I think you could have like 50 megs, you could have a gig. It'd only be like a couple cents to do so. And I'll even show it right now. Like if I go ahead and hit this publish keys button, oh, we see this MetaMask notification. And sure enough, you'll see it's a contract interaction, and it costs 3 cents. So it costs 3 cents worth of Ethereum to publish this chunk of data to the contract. It says $0 up here. It's actually a glitch because I'm not using real Ethereum. If I was using real Ethereum, I'd be broke by now. I think I've wasted about $200 to $300 worth of Ethereum testing this application. I'm a pretty bad developer myself, but you can just go ahead and hit confirm, and once you do that, there should be a little pop-up here that says your transaction went through, so your key's been broadcasted. But if you don't see that, you see I have Ganache down here. I mentioned earlier that simulates your blockchain. So if we go there, you're going to notice, oh hey, look, There's a contract call here, there's a transaction hash, and if you really wanted to, you could see the internal data, but that doesn't really matter. All that matters is once you see that, you know data's been transmitted to the blockchain in the form of a transaction. Now, one of the things I want to get right off the bat is when you send or store any data to Ethereum, you're going to have to pay up. But if you have to get data, that's free. In fact, in the actual code for the smart contract, you're going to notice this keyword here that says view. And view just tells the contract or the person calling the contract, like, this is free. You won't incur any costs. It's a bit of overhead optimization for you. But if you see anything else like this, like it takes some memory and it doesn't have view in it, it means it's gonna incur some cost. You can transmit, and if you wanted to send a file, well, I go ahead and I could get a recipient's Ethereum address, which is already linked to a public Ethereum address. Go ahead and slap that in there, and you choose your private key. It'd be this, and yes, it does look terrible. I know, like, oh wow, look at me, I'm copy pasting passwords. Very poor security practice, but it's a very good illustrative example nonetheless. You choose a file like this, and then you go ahead and click submit. I mentioned earlier, you saw this chunk of code here in, oh yep, see, there we go. So to actually send the file to that person, I only have to pay 6 cents. Now, that sounds terrible for a picture, like, oh, I have SMS, I just send a picture for 6 cents. I mean, that sounds terrible. But let's imagine I have 50 terabytes worth of something. I can send it, it'll still be 6 cents. And the other person, and only that other person, can access it. It's very doable. So I go ahead and hit confirm, and I've just burned my 6 cents worth of, fake Ethereum. So going back to that JavaScript, we saw the publish key function. And that's like when I clicked that button in the beginning that pretty much said publish keys, it just triggered this function. And you'll notice we have that contract instance that I pointed out earlier right about here. Your contract instance, which is based off Web3. All you needed is your address and your ABI. And then you can console log and you extract the information you need. But anyway, let's go down and let's go back one more step, and I'll show you what the actual Solidity code looks like. So to build these smart contracts, it's very similar to how a normal compiler works, like a C and C++, they all go down to assembly. Well, for smart contracts, there's actually a base assembly language. I don't encourage you to try and program in that language, but it is there, because the way Ethereum works is every node is almost like a little miniature stack machine. In fact, if a modern Intel CPU has around, I think it's a couple thousand, maybe 10, 50,000. I know because the Intel developer manuals are a couple thousand pages long. The Ethereum virtual machines, or the stack machines, are only 32 instructions at most, very light, but still very powerful for the concurrency they offer. So the language that I chose to use is Solidity, and Solidity gets compiled into that stack machine language, and then it gets executed across all the nodes simultaneously. There are other alternatives. If you don't like this language, you can check out Viper, but I must caution you, Solidity is probably, I would say, the de facto language at this point. So we go ahead and I mentioned earlier that we want to store those public keys. So we have what's called a mapping here. It's very similar to a dictionary. Why am I even saying it's similar? It's identical. It's completely identical to a dictionary. And I pretty much say that, okay, we take an address, we take an Ethereum address, and we map it out to an unsigned integer array. Each element being 8 bits or a byte, unsigned. So each element would be like 0 to 255. The reason we do that is because the way Salt works is your key that we saw earlier, this public and private key, these are all supposed to be unsigned 8-bit arrays. So we're gonna push that to the contract. There's a mapping there. And then we have another mapping here. It takes an address, but from the address you get the encrypted data. And the encrypted data has the box, which you took the public key, you took your picture, and you took your private key. And you'll see why that private key needs to be in here pretty soon. And you went ahead and packaged it. So now it's in this nice little compartmentalized structure. And then we have all these functions here. And I must note, like, this is a very small file. It's only like 38 lines. In 38 lines, you can build something that sends massive files over over a decentralized network. So if you had 100 lines, or I'm trying to emphasize like the amount of labor required to make a decentralized application is not that hard. It's not that different from making your own React.js or Node.js application that runs on some centralized server. But you will have to think very carefully. I give an example why. You'll notice this memory keyword. So you've got a function declaration and you have your memory keyword here. And that pretty much tells the contract compiler, like, reserve a chunk of memory for me, but don't price me for it, because it's just reserved, but it's not going to incur any costs. These mappings and doing this, like assigning a chunk of data to some area in that mapping, will cost something, because I think if I can see, okay, oh, you see this, there's a tiny little number here, and it says gas used. So most of you are familiar with the fact that Ethereum is, the unit of currency for Ethereum is Ether. But there's another unit of execution, and we call that gas. Every line of code, every operation costs some amount of gas. And this is mostly because we want to, like a lot of, like Bitcoin, when you send a transaction, there's a cost associated with it. The reason that we implement this cost is for a very simple economic reason. By implementing cost, you deter possible attackers. There's the idea with proof of stake, like, oh, you have to own a couple $1 billion worth of crypto. I don't know about you, but unless you're like Escobar or something and you really have like money to blow, it's not that worth it. So that's why you have this cost thing in place. And gas is inherently linked to some number of Ether. So 200 gas might be worth this much Ether. So the price of the US dollar to Ethereum is volatile. It changes. That's just how the market works. But the number of gas to Ether is fixed. That stays constant. It stays the same. And you'll notice, like, oh, this thing that I did, broadcasting my key, that took 116,454 gas units to do so. So that translated to 3 cents worth of Ethereum when you saw the MetaFox plugin pop up. So you set your public key. You can get a public key too. So I mentioned how if you have someone else's Ethereum address, we go ahead and set their public key. Well, now you can get it as well. And it has that view option here, meaning that there's no cost incurred. It's public, meaning that anyone can use it. I could set this to private. If I set it to private, it means that you can only other contracts can call it. Like, it's only available within the Ethereum ecosystem and nowhere else. And you see that this goes ahead and takes a key, an unsigned integer. If we want to actually send information, like I mentioned, we go ahead and send that file to our friend. We're not actually going to send the whole file. I mentioned earlier we had IPFS, or the Interplanetary File System. We go back to our JavaScript, and you'll notice I have this little line right here. New Internet Protocol File System, Interplanetary File System module. That's where we're actually going to put the data. But every time, regardless of how big the data you upload is, IPFS returns a guaranteed unique hash for that piece of data. So I go ahead and grab the hash, and I just submit it to the contract as another unsigned 8-bit array, and you've pretty much secured the hash there. The reason I keep mentioning unique is the fact that if we were in person and I just gave you the hash, it'd still be pretty secure. It's not like a URL. Like if I type Google here, I'm going to get to Google. If I type Google somewhere else, I'm going to get to Google too. But with IPFS, you need that unique hash. There's no other alternative to it, because it's not location-based addressing. It's content-based addressing. You ask what instead of where. So we have that. We have our encrypted data struct. So the box is the encrypted data. The nonce is a little trickier to explain, but it's pretty much like if you're in a hurry to make soup, you pour more water into it. I know I'm a terrible cook, but on the surface level, hey, it's the same amount of soup. So that's the nonce. That's a little the extra water that you're going to go ahead and add in there. And you have to make sure that the nonce stays the same for the person sending it and the person receiving it. Those are the two crucial pieces of data they need. They need the box, and they're going to need the nonce. So I go ahead and I set this temporary data structure, and I send it to the receiver's address. And if you actually want to get the data, well, all you have to do is go ahead and get the sender's address and put in your box and your nonce. And the reason we get the sender's address when we want to say like get data is because from the sender's address, we get that public key someone mentioned in the beginning. And from the public key, that's where I get the, that's where I can actually decrypt it in the Salt crypto system. All right, so that's our Solidity contract. It's literally, how many lines? 38 lines. So pretty small, pretty compact. But you're probably curious, like, well, that's great and all, but how does this contract relate to what I showed you here? This is not the actual Ethereum network. This is called Ganache. For those of you who want to get into Ethereum development, I highly encourage you guys to install it. And it simulates the blockchain for you. So if I were to open up my terminal here, and in the repo, you will notice that I have two folders, back and front. I make a distinction between our back end, which is the Solidity, and the front end, which is the JavaScript and that terrible looking HTML you saw earlier. So if we go into that directory, SFTR back, and then you're going to go ahead and like all these folders here, that's made by Truffle. Truffle is the tool you use to make that contract ecosystem. If you go to an empty folder and just type in Truffle in it, it'll set up the environment for you, so you can easily compile and run your contracts. So if we go ahead and type Truffle compile -all, the all flag forces the compiler to compile everything. The compiler by itself it uses lazy compilation by default. So if it detects like something was already compiled before, it'll just skip it, even though you might have already changed something. So then we go ahead and hit that, and give it a quick second. It'll do its magic, and it says, all right, so it compiled, and our all of these Solidity files end in .sol, and it compiled to this contracts folder. We go ahead and just see our context, so nothing really happened. There's a special file for Truffle called truffleconfig.js. If we go in there, this pretty much tells Truffle to push the contract to Ganache instead of the main network. So I pretty much say like, okay, here's the port. You can find the port in the Ganache settings. You just go to Ganache preferences, and yeah, see port number 8545. You just go ahead and align the data. I have a wildcard for the network ID. I only have one Ganache instance, but if you have like a custom network config, you can put the 4 8s that I put there, and you can pretty much run it from there. So we go back. Let's go ahead and cancel. And if we want to get the contract onto the Truffle or Ganache environment, pardon me, Ganache, we want to get it onto Ganache, we just do Truffle migrate. And it should, okay, it says network up to date. That means the contract has been pushed to the blockchain simulator, which is Ganache. And you'll notice like in my application, I did have in the JS here, I had this ABI and I had this address. So where do I get the binary interface and where do I get the address of my contract if it's being simulated? Well, you don't have to worry about that, because if we go back to that folder and you go into contract or build, your build folder, and you go ahead and go into contract right there, and we go ahead and just hit more SFTR. I actually have it open here, more colorful. Excellent question. We got a question about what the difference is between the contracts directory and the build contracts directory. So the contracts directory is where you put your source files. Like that's where I put my .c or .sol files. The build folder is where all the compiled stuff goes. And it's also where the compiler gives you a JSON file. And in the JSON, you see all the data that you need. Like here's the ABI. I just copy and paste this into the JavaScript. And then if I scroll down a bit, you have networks, and then I have, oh, there it is. That's the address that my contract lives at. All I need are those 2 snippets of the data, and I can slap that right into the JS file. And I've gone ahead and I've done it. That's pretty much all you need. I think you had a question earlier, or no? Okay, cool. Have I lost anyone yet? Everyone's still hanging in there? Okay, good. Feel free to ask questions. So we have this implementation for like getting your public key and pushing your public key. We also have this function. This is pretty interesting. So this is how you actually upload your file to IPFS. Now, we're not running our own node. We're basically sending data through the Infura network. If any of you have taken Japanese, my terrible pronunciation, it's supposed to mean infrastructure. Infura, that's how I remember it. But we have access to a gateway, infura.io. So what I do is I go ahead and take your file and I send it through that gateway, and it gives me a unique hash. I think I can pull it up. Okay, there we go. So this is IPFS, and let's see if I can. Yes.
Is the hash column kind of like a location address?
So we got a question here about asking, like, can you think of the hash as like a location or like a URL, right? Something like a URL or something to find. Yes, you can think of it that way. It's pretty much like a resource identifier. You know, URLs, uniform resource location identifier. I think that's or URIs, but it's the same idea. It's very similar, except instead of saying where to go for something, like a URL is like, oh, you know, if you use like a DNS server, it'll say like, oh, this URL maps out to this server location. IPFS totally forgoes that. We just tell the network, like, here's a hash. Does anyone else have the same hash? And it sort of gets broadcasted throughout all the other IPFS nodes until a node says like, hey, I have the same hash too. Why don't you go ahead and give me the data? So that's IPFS in a nutshell. But you will note there's no DNS server, there's no centralized entity, because that picture of me that I uploaded could be on someone else's node. And because once you get data from the node, you store a local copy by yourself. You can do that in JavaScript, like launch an IPFS node, but I intentionally did not do that. One, to keep things easy, and two, because I don't want my decentralized app eating up 98% of your RAM and then dropping random files. It's a safety concern. And then we have upload file. I should probably give the heads up. All these functions you see here are mapped to the buttons that you saw earlier. Like this is your jQuery. You had your generate keys, publish your keys, you upload your file, and you download your file. So that's like, it's just 4 lines of jQuery. The reason why I have it set up this way is because I originally tested this in Node, but I really love this require thing. Like, this has saved my butt so many times. So there's another JS thing I mentioned earlier in the PowerPoint. It's called Browserify, and Browserify lets you use statements like these, but you just it recursively digs up all the libraries you need and includes it in one neat little package. Because if I did like vanilla JS, I couldn't do this require statement here, because these all grab the Node modules. Yes, these all just map out to your buttons. And I figured I should probably go into more explanation about that private crypto system. I know there was a concern about why we even need that private key, so that's what I'm going to show right now. So after all these disgusting callbacks, and I apologize, I'm a little biased against JavaScript. It's asynchronous execution. Like that's the biggest joke of the 21st century. But anyway, if we go ahead and instead of going to download file, we go to upload file. Okay, here we go. So in those fields, I say, we get your private key, and you have this this field here, so that those random numbers you saw earlier, they get turned into your private key. We get your file, and here's how we get your hash. We take the file that you upload, like I uploaded a picture, and that file gets converted into a blob. It's quite literally called the blob object, and that blob later gets it gets uploaded to IPFS, and it's a very painless process. Yeah, it gets buffered, and then IPFS upload, just that one function. I have it in the demo code. If you want to use IPFS in your project, you can go ahead and rip that function if you want to. Okay, now here's how we actually get the key. So so I got we have a constant here that we want the sender's public key, i.e. my key. I'm the sender, so I get my own public key. And I mentioned earlier that your private key is mathematically related to your public key. So that's why I put in my private key, and out comes the public key. Pop goes the weasel. The nonce is just a bunch of random bytes. It's the water you add to your soup, so you have enough soup. And one of the reasons we do this is because there is a known vector of attack, where if there's like a correlation between, like I have King James's Bible, no no religious antagonism intended. But 5 King James's Bible, and my hash is like really long, but then I have hello world, and my hash is really short. You see how you can sort of, it's very possible to mathematically reverse from that information. You can infer like, oh, you can infer the file contents, and it's definitely a vector of attack. So that's why you should always, 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 always have this nonce with you. You're going to have to give this nonce to the receiver as well, but if it's publicly transmitted, it's okay. Like if the attacker gets the nonce, no worries. What you do have to worry about the attacker getting is your private key. That's the only thing you have to worry about. And then you make your box. So I've taken my file and I've turned it from its blob format into so I decoded it into just a bunch of numbers. It's another uint8 array that you saw earlier. And I can upload that. I can upload all of this in its entirety as the box into the contract, because I do have a mapping here that maps your address to the encrypted data. So you see how when you're planning out your decentralized applications, you're going to have to jump through like different levels of the application itself. And then when you send your data, you'll notice I have a contract instance and I can call send data. And what's really neat is there's a one-to-one correspondence. Like this contract instance, this function here, and your Solidity, send data, one-to-one correspondence. Actually, I lie a little bit. I lie a little bit because there's this callback function here you have to have. It's enforced by Web3. This pretty much just makes sure that if your data doesn't come back properly or something happens, you'll know. Like you have some contingency plan in place. And you can see my contingency plan is to kill the program and just print out the error. I just want to build the simplest possible version. I'm not going for fancy or anything. So that's my contingency. You console log everything. And then you have your get contract data, and that uses like the similar system. Like you need the person who sent it to you. You need their address to get their public key, and then you use your private key, and you can go ahead and decrypt the data. And when you decrypt the data, you're not going to get the whole file. You're just going to get the hash. Like you see decode payload, and that payload came from the box. And the box, well, you got the box from this guy, get contract data. It's this like a Russian nesting egg doll problem. But once you do get that data, you can decode it, and it's not going to be the actual file because I told you how IPFS works. You get a hash back, and from that hash, you can grab the file regardless of how big it is. And once again, I want to emphasize, it cost me 3 cents to publish my key, and it cost me 11 cents to publish the hash. And hashes, by their mathematical nature, always have a fixed length. They should have a fixed length. If they don't have a fixed length, ditch that hash function. That's considered compromised or very poor design. So from your hash function, you can grab the file. You can use the same API here, that IPFS portal from Infura, and you can go ahead and grab your key. So keeping things short, that's Sifter. That's how Sifter works. It's just a public and private key. It's a file. You can send and receive it through the Ethereum blockchain. But you'll note that it's when you build these applications, it's always an exercise in the sleight of hand. Where do you actually store that data? So IPFS provides like a really neat portal. But anyway, I digress. I know you guys have had your fair share of looking at this terrible HTML and probably even worse JavaScript. But I hope I've given you some tools or some ideas to play with. Oh yeah. I won't be sending out the slides. I mean, it's pretty sparse, but you do have the repo. Oh yeah, we found a potential security vulnerability. This doesn't come. I don't think it comes from Salt. It's another library that's using an outdated npm library. You can fix it yourself if you really want to, but they're going to fix it pretty soon. I only had it in there for the sake of convenience. Yes, I can do that. I can do that. Oh, if they're, yeah, I'll post the slides anyway. Huh? Pardon? Yeah. I'll definitely do that too. I will admit I was in a bit of like a rush earlier this day to make sure everything worked out and the code checks out. Oh yeah, I do want to give a very quick heads up. If you are trying to get this receive file chunk to work, it won't work, and I'll tell you why. The Salt library gets a little finicky with some of the asynchronous calls. You might have to go in there yourself and make sure all the data loads properly. But other than that, I mean, I think you guys know how easy it is to send data through IPFS and how to bridge your smart contract to your front end with Web3. And it's this little guy here. Do we have any other questions? Yes. Yes, we have an excellent question. It's still like, is it still prone, like you cite man-in-the-middle attacks, and that is definitely a vulnerability. But it's only a vulnerability if you're transmitting the key over the network. There are ways to make sure that, like, even if I copy paste the private key, it won't get it shouldn't get compromised unless like you're a high-profile NSA target and like your key's been bugged or something. In which case, like that's out of the picture. That's out of the picture. But I do understand your concern. That is another safety practice. Never send your private key without some form of encryption, or you should ideally have it stored on paper somewhere. That's why like you see these Bitcoin wallets and they tell you like, oh, print out your private key and store it somewhere safe. Because as long as something exists digitally, it can get compromised. Have any other questions? All right, well, thank you so much for coming to this workshop. I really appreciate all you guys coming out. This is the first time I've hosted a workshop. I do apologize in advance if it seemed like really circuitous or bouncy or kind of too many non sequiturs. But I hope from that repo and some of the code examples, I can give you a little idea of what really goes through like a decentralized applications designer's head, like the amount of planning required and the general skeleton structure, because you saw there were like multiple files. You saw that it was, we have to definitely, make sure everything checks out, because real money is, changing hands here. All right, well, without further ado, I think you guys have some ice cream you guys might want to check out, or free t-shirts. Thank you very much.
I'm bringing Philosophy.